And let's move on to the last part, which is about model evaluation. So after we have visualized our simulation data and we want to check if it is accurate or if this is, the simulation is correct or if it is accurate enough. So we want to compare our simulation results with observation data or the ERA5 reanalysis data or any other kind of reanalysis data. So here we want to introduce some methods to do the model evaluation. And these are the libraries that we will use in this session. I think these are the libraries that we first introduced. So basically it's the interpolate and the statistics function from the CPAS. And before we move on to the whole evaluation thing, we need to first introduce the interpolation, the concept of interpolation. So when you have, so let me draw something. So when you have a simulation result, it is in a field here. So you have something like there are a bunch of cells here, a bunch of cells here. So maybe I just use it. I just do a structured way. I don't want to do it in unstructured way. Okay, these are the data, right? So these are the data points and you have a bunch of data points in these here. And somehow you have an observation data here. So if you want to check if your simulation result matches the observation data, you will need to interpolate your simulation data to this point. So you make use of your simulated data around this observation point to interpolate to this position so that you can compare your simulation data with the observation data. So this is basically the concept that we want to use interpolation for our simulation data. A clear image. Clear all drawing, okay. So interpolation, this is a mathematical concept if you do it in a math way. And let's visit, okay, sorry. If you visit this website, you can find the documentation from the CPAS interpolation function. So it supports many different types of interpolation. So I even don't know all of them here. So you may, if you are really familiar with interpolation, you may know this. And here I have 1D data. So 1D data is basically only have XY axis. And so it's basically a 1D function like y equals to mx or something. So when I apply the interpolation function, okay, I'm sorry. So here interpolate is from this package, okay? So you can find the function like inter 1D for the 1D interpolation. So here are a few of the parameters that you need to add to the function. For example, you need the x-axis and the y-axis, the data here, and you need to specify the kind of interpolation. For example, it's linear or neighbor interpolation or less blind interpolation. Actually, I don't really know all of them, but if you can see here, I plot all the data here, and then you can see here from the plot, different interpolation method can generate different line functions. So if I use linear function, it just connects all the points, all the given points here. And then if I use the neighbor function, it basically only find it generates the same value for its neighboring grid here. So it's x-axis, and then for the neighboring x-axis for this point, it just generates the same y value. And for this spline interpolation, it has it helps you to generate a more. So this is basically a more advanced method for interpolation. So it basically it helps you to find a most suitable function for these data points. So these data points are actually from the sine. This is basically a sine x function, and I extract only these data points here. So from these data points, if you use this kind of interpolation, it helps you to generate a function that best matches these points, which is basically a sine function. So you can see from the green line here, if you use a linear function, it's a linear line. But if you use this function, this interpolation method is something curved here. This is a sine function. So yeah, so this is the basic idea of some basic methods for interpolation here. And for the multivariate interpolation, so here we apply interpolation to the 1D data. So you can see it only has the y values, but for multivariate interpolation, you need to interpolate it with respect to the x-axis and y-axis. So it is what we need to do for our simulation data as well, because our simulation data is like also have a 2D coordinate. It's in xy dimension, and it has value in the x-axis and the z-axis. So this is what we need to do for our simulation data. And I just take this interp 2D from the CPAS function as example. You also have linear method and the cubic method for this multivariate interpolation. So here firstly, I generate a bunch of data points. So this is the coordinates. So I just set the coordinates as 0 from 9 and skipped it by 1 in each of the data points. And then I assign a value to each of the data points. So you can see the data points are this one, this one. And if I apply the linear interpolation, it automatically fills the values in between these for you, and using the linear method. And here cubic spline is also the same. So, but you can see it's more, so this is more smoother because it recognizes the sine function that the data point has, and then it uses the interpolate the data with the sine function. Yeah, so this is basically some of the basic methods for the multivariate interpolation. And here we introduce a new method called barycentric interpolation, which is most suitable for our simulation data. So what this interpolation method do is that, so let me draw some diagram here. So in our simulation data, we have these hexagonal cell, right? So for example, I maybe just kind of, okay, maybe something like this, okay? We have simulated data points in these cell centers. So I call these ABC, okay? Just follow the graph. And then we have maybe an observation data here, and I call it P. So what we are doing is draw a triangle between these cells and then link them to this point P. Okay, and then you will have, in this triangle, it will be divided into 3 different triangles that has different area. So it's like X, Y, C. I just follow this graph here. So these areas determine the weight that you apply for each of the data points. So you can see this equation. So, well, because A is obviously closer to this point P, right? So you need to apply a larger weight for this A. And then this will be the weight of this area of triangle. You can see this has the largest area for the point A here. Yeah, you just apply. So these X, Y, C are the weight apply to these ABC points. And after you apply this equation, you can interpolate this point from this information surrounding this point. So this is basically the idea of barocentric interpolation. Do you have any question with this method? Okay, I think not. Then let me clear my drawing and let's move on. Okay, so and I also want to, this is another thing that I want to remind you, because in our simulation data, it is like this is in spherical coordinate. This is in Earth, right? So the ABC points are actually in the spherical coordinates. So the geometries will be different. So in a plane coordinate, the ABC is just like a sphere. So this is like a plane triangle, right? But in a spherical coordinate, the triangle will be something like this. So like this is the whole sphere, and then this is the center, and then you have something like this, right? So the geometry is a bit different here. So yeah, so it is very difficult to introduce the whole thing to you. So we just wrote up the whole barocentric interpolation function to these scripts. So you can just apply these scripts for your, maybe if you have done some simulation result and you want to interpolate to some points and then verify it, you can apply these scripts. And let me demo it once here. So I have the simulation outputs from the die.nc here. I just use the same data from the demo compass, and I read it using the OpenM dataset here. And I also read the grid, the grid.nc here. So in this interpolate script, so first of all, you need to find these two .py from your folder. So let's go to the Jupyter server and then go to tutorial 3. You can see these two .py here. Okay. And then you need both scripts in the same directory as your Jupyter notebook. So so the system can find the .py for the interpolate.py. Yeah. So this is basically from the interpolate.py, and then it imports a class object from this script. And so apply this object to the grid, and then this is the output, right? So this is the variables for the output, and then I put it to this class object, and then it creates an object here, interpolate here. So here so this is the object created from this thing, and then I need to apply the interpolate function to this object, and then specify the latitude and longitude that you want to interpolate, that you want it to interpolate to. So this is I think this is the coordinate of HKO station. And after I interpolate it, it generates a dataset object. So I just put it to the DS here, dataset here. And you can see I display this dataset. And so this is the interpolate result. And you can see the dimension, it changes to n records because it only has one set of latitude and longitude. So it only has one record. You can add more points when you need it. And you can see all the data variables are interpolated to this particular point, and it only has dimensions of time and the m record of that coordinates. So this is so we recommend you to do barocentric interpolation to your simulation data because it uses most of the information from your grid. It uses the information from the 3 neighboring cells of the observation point that you have. So yeah, this is the idea of interpolation. and how you do barocentric interpolation.